good morning dear students. Welcome to Gundachandra Higher Secondary School. Okay, so in this session we are discussing about a very important part, that is moving coil galvanometer. Is a very important device in physics. So this is the pictorial representation of your moving coil galvanometer. Okay, this is the cross-sectional view. So we will come to later on. So first of all, this is moving coil galvanometer. First of all, we will discuss why the moving coil galvanometer is required. Okay, and what is the significance, what is the use of your moving coil galvanometer. Clear all of you? Okay. So first of all, moving coil galvanometer is a device, okay, which is used to detect, listen very carefully, moving coil galvanometer is a device which is used to detect small amount of current in the circuit, okay, small amount of current in the circuit, and also it helps to give the direction of the current, in which direction the current flows. Clear? Okay. So moving coil galvanometer is a very important device which is used to detect, very important, which is used to detect small current, small amount of current, and it gives the direction of the current. Clear? Okay. So this is the main important use of this one, and there is another use also, that this moving coil galvanometer with some simple modification, the moving coil galvanometer can be used as a emitter and can be used as a voltmeter. How we will talk it? We will talk in the later. Okay, clear. So don't worry about that one. So in the first we will discuss that in a moving coil galvanometer. What happens actually? Okay, so we know that it is a device. It is a device which is used to detect the small currents, the small amount of current. Listen very carefully, because there is a device also to measure the current, that is called emitter. That is called emitter. But it is no. But the difference between a emitter and a volt and a galvanometer is that emitter used to measure the current. Clear? Emitter is a device which is used to measure the current, whereas the galvanometer is a device which is used to detect the small currents, the small value currents. This is the main difference between a galvanometer and a emitter. Clear? Okay. So this is here. Now come to our construction part. Let us see how the moving coil galvanometer construct. Clear? So all of you look at the figure very carefully. This is the structure. That means if we will cut the cross-sectional view of a moving coil galvanometer, then it looks like that. Okay. So what happens actually? What it consists of? Look at here. A moving coil galvanometer first of all consists of a permanent magnet. Okay. The moving coil galvanometer consists of a cylindrical core which is made up of soft iron. A cylindrical core made up of soft iron. Look at here. If a cylinder, suppose this is a cylinder, all of you look at it. Suppose this is a cylinder. Okay. So if I will cut it, or if I will take the cross-sectional view, then how it looks like? It looks like in the front it looks like a circular one. So don't worry about that one. Okay. So that's why the middle portion, this one, the circular one, this is actually not a circular. It looks like circular because it looks like circular because we take the cross-sectional view of a cylinder. That's why. So actually, in practically, it is a cylindrical in nature. Okay. So this is a cylindrical core which is made up of soft iron, and on the cylindrical core, a coil is wounded over it. A coil is wounded over it. Okay. Which type of coil? A rectangular coil. That means, suppose this is cylinder, or look at it, then you can easily verify. Suppose this is cylinder, and from this side we will wound a coil on it. Okay. This is the view. Understood all of you? Okay. So this is your cylindrical core on which a rectangular coil, I will mention here, this is a rectangular coil which is wounded over it. I will just draw the three turns here, but don't worry, the turns are repeating to the whole cylinder. Just I have to just for drawing purpose, okay, I will draw the three turns of it, but actually the coil is wounded to the whole the cylinder. Clear all of you? Okay. So now the one end of the cylinder, listen very carefully. The one end of the cylinder is connected to a spring, okay, and another end of the cylinder is connected to a pointer. Understood? Okay. So this spring, one end of the cylinder is connected to a spring. What is the function of the spring? What is the function of the spring? I will talk to you later on, because the spring having a very vital role in the moving coil galvanometer. Clear all of you? So first of all, from the structural point of view, what we will observe here, we observe here that there is a cylindrical core. On the cylindrical core, a coil is wounded over it. Okay, number 3, one end of the cylinder is connected to a spring, okay, which helps to pivot. Okay, now another end is connected to a pointer, which this pointer, what is the function of the pointer? The pointer helps to, okay, helps to deflect on the scale. The pointer helps, okay, deflect on the scale and to give us the measurement, the amount of the small current. Understood? Okay, and the whole structure is present within a magnetic field. Look at this figure very carefully. Which type of magnetic field? A radial magnetic field. All of you can observe from the figure. Because why it is radial in nature? Because here, look at here, we are using a magnet, a permanent magnet, in which shape? A concave shape. Look at here. This is a concave shaped permanent magnet. Due to this shape, concave shape, we can generate the radial magnetic field. Okay? Because if the magnetic field becomes radial, what do you mean by radial magnetic field? Because the magnetic field passes through the radius. This is the case. Understood all of you? Okay? Just I want to small modification here. Look at it very carefully. Then you can easily visualize that one. That means, look at here all of you. From the North Pole, look at here. From the North Pole, okay, the magnetic field lines are generated, okay, and it will end at the South Pole. It will end at the South Pole, and these field lines are passing along the radius. That is very important. That's why the magnetic field is radial in nature. This is the main important part, because this is radial. This is passing through the radius of the cylinder. Yes or no? Okay. So these structures is radial in nature. That's why the magnetic field. And to generate the radial magnetic field, we will take a concave shaped permanent magnets. Okay. And why we will take the radial magnetic field? The reason is that the radial magnetic field will generate, okay, more magnetic field in the core part, which helps to, listen very carefully, which helps to measure the moving coil galvanometer perfectly. This is the reason behind it. Why we will take the radial magnetic field. Understood? They are generating from the North Pole, ending at the South Pole. Very simple. Understood? Okay. Now this is the construction part. Understood all of you? This is the construction part. What they construct? First of all, again I will repeat. They consist of a permanent magnet, concave shaped permanent magnet, number 1. Number 2, it consists of a cylindrical core which is made up of soft iron. Okay. Number 3, on the cylindrical core, a rectangular coil is wounded on it. Okay. Then there is a spring. One end of the cylinder is connected to a spring which is pivoted, another end of the another end of the cylinder is connected to a pointer, okay, which helps to detect on the scale. Understood all of you? Okay, and the magnetic field providing here is which type of magnetic field? Radial magnetic field. Understood all of you? Clear? So this is the structural analysis. Now come to the principle. So what happens? So listen very carefully, when the current flows in the coil, okay, then what happens? When the current flows in the coil, we know that from the previous video, the previous discussion, we know that when a current carrying conductor is present within a magnetic field, then it will generate a torque. In the previous classes, we know that it will generate a torque. The similar thing happens here. So this is a coil which is wounded over a cylinder. Okay, and when it is present in a radial magnetic field, then the coil will generate a torque. Clear? So what is the value of torque? The torque tau is equal to, we know that is the magnetic moment M cross B. This thing we have already derived, the cross product between magnetic moment and B. So what is the value of magnetic moment? The IA cross B. Understood? Clear? And listen very carefully. To this coil, and repeat, to this coil, the radial magnetic fields become perpendicular in nature. That's why the cross product between these two, what I can write? IAB sin theta. Okay, and as this radial magnetic field is perpendicular to the coil, that's why the angle between them is 90 degree. Okay, so that's why IAB sin 90 degree. So IAB, because sin 90 is 1. Understood? Okay. Now there are how many turns in the coil? N number of turns. Let there are n number of turns. N turns in the coil. So that's why torque is equal to N A I B. So this is my torque. Okay. So this is my torque generated. Again I will repeat. This is my torque generated in the coil. Understood? Okay. So due to the torque generated in the coil, what happens? The cylinder will rotate. Understood? Due to the torque means rotation. So the torque which generated in the coil, due to this torque, the cylinder will rotate. Understood? Okay. So now we know that one end of the cylinder is connected to a pointer and another end of the cylinder is connected to a spring. Now the vital thing is there. So when the cylinder tries to rotate or tends to rotate due to the torque, okay, then the spring will take part. So what happens in the spring? The spring provides at this moment when the torque is applied on the cylinder. Listen very carefully. When the torque, this amount of torque, NAB torque, is applied on that cylinder, at that moment another torque that is called restoring torque, is produced in the spring. Understood? Okay. So what is the function of restoring torque? Now all of you know that restoring means again coming to the normal position. So that's why the spring helps. So when the cylinder rotates, the pointer will move from this point to this point. So if there is no spring, what happens? The pointer can move to this side also. But this is not possible. Okay, this is not practically possible. So to avoid such type of condition, to neutralize this torque in the cylinder, there is another torque produced in the spring which helps to to neutralize this torque or to equilibrium this torque. Okay, so that torque which is generated in the spring, that torque is called restoring torque. So the torque generated in the spring, why? To neutralize, okay, neutralize the torque in the cylinder. Understood? To neutralize the torque in the cylinder or cylindrical coil. Understood? Okay, so that's why now that torque which is generated in the spring, that torque generated in the spring is called restoring torque. This is a very important concept here. Okay, so restoring, as there is a, we know that from the first year analysis, there is a restoring force. Similarly, the restoring torque. Okay, so what mean by restoring? It will helps to get to the original position. So when the spring, due to this torque in the cylinder, listen very carefully, due to the torque generated, this amount of torque generated in the cylinder, the pointer rotates. Okay, so to again return to the original position, the restoring torque helps. Clear all of you? This restoring torque which is generated in the spring helps to the pointer to come to the original position. Understood? Okay. So now this restoring torque, what is the value of this restoring torque? Look at very carefully. What is the value of this restoring torque? Suppose we will take, this is the tau restoring. Okay, tau restoring, that is equal to this restoring torque generated in the spring. Tau restoring value is that is equal to c into theta. That is equal to c theta. So what is actually theta? Theta is the angle of twist. How much the spring will twist? That is the angle of twist. And what is c? C is nothing but couple per twist. For one twist, what is the value of couple? That is the value of c. For one twist of the spring, okay, what is the value of this couple? That is c is the couple per twist. Theta is the angle of twist. Okay, so now in equilibrium condition, these two must be same. To neutralize or to equilibrium condition, these two torque must be same. That is the torque generated in the spring and the torque generated in the coil. Okay, so now here you have to write. So in equilibrium condition, we have to mention here in equilibrium condition, in equilibrium condition. Okay, so in equilibrium condition, what happens? Now the torque generated in the spring, your coil, okay, must be equal to the restoring torque. So that is equal to, okay, so now this is nothing but your N A B I, just, okay, N A B I, that is equal to C theta, because restoring torque just equals C theta. Understood all of you? Okay, so that implies theta, that is angle of twist, is equal to NABI divided by C. Clear? So we have to just rearrange it. That is NAB divided by C into I. Clear? So this is what we have accumulated. NAB divided by C. That is a very important. That is a constant actually. What is that constant called? K. That constant is called K. So here you have to write where that K constant is your NAB divided by C. That is a constant. What is that constant called? That constant is called galvanometer constant. That constant is called galvanometer constant. Okay, so theta is equal to K. So here it is a constant. So we can write the theta value is directly proportional to deflecting current. This is a very important one. So we can write as K is a constant. So we can write the theta, that is angle of twist, is directly proportional to the current flowing through the coil. As the current increases in the coil, the theta value also increases. And vice versa, that is when the current value in the coil decreases, the theta value or the angle of twist value also decreases. Understood all of you? Clear? Okay, because that value, that is number of turns, area of the coil, magnetic field, and the couple per twist, that is a constant. That is constant for it. Clear all of you? Okay, so that's why the angle of twist must be directly proportional to the deflecting current, which helps to deflect, or current flowing in the coil. As simply I can tell current flowing in the coil. Okay, so if the current increases, angle of twist increases. If the current decreases, angle of twist decreases. Very simple. Understood? This is an equilibrium condition, and this equilibrium must be maintained in a moving coil galvanometer to get the proper deflection in the pointer. Understood? Okay. Clear all of you? So this is how the moving coil galvanometer works. Understood all of you? This is how the moving coil galvanometer works. Next part. In the next part, let us know. I told you in the first. Okay. So let us know how a galvanometer, moving coil galvanometer, can be used as a emitter, or can be converted as a emitter. Let us know. So galvanometer is emitter. Okay. Let us know how a galvanometer can be converted or can be used as a emitter. What modification we will do in the galvanometer so that the galvanometer can be used to measure the current. Okay, so let us. So what we will do? Look at very carefully. So we will first take a galvanometer. Suppose this is a galvanometer G. Okay. Now to convert the galvanometer into emitter, listen very carefully. To convert the galvanometer into emitter, so what we will do? Now we will connect a resistance in parallel with the galvanometer. We will connect a resistance in parallel with the galvanometer, and important part is that the resistance value must be low or small. The resistance value must be small. Let us name the resistance as S, or shunt resistance. The S is nothing but shunt resistance. Understood? Okay. So now this structure, whatever I have done here, this is now a emitter. Very simple. Okay. So what we will do? What we have done? Now we will connect, or we connect a small value resistance parallel with the galvanometer. Understood? Okay. So now this is suppose the current I, and Ig is the amount of current passing through the galvanometer. Then what is the value of current passing through the shunt resistance? Now I minus Ig. Very simple. I minus Ig is the amount of current passing through the shunt resistance. Okay. Now our aim to find out the value of shunt resistance. So what we will do? Now we will compare. So what we will compare? Now applying. So we will apply the Euro KVL, which is voltage law. Okay. So by applying KVL, which was voltage law. Okay. So what you will get? The amount of voltage here. What is the amount of voltage? Now we know that V is equal to I into R. So what is the resistance of the galvanometer? The G itself. So Iz, the amount of current passing through it into the resistance Iz is equal to, what is the current passing through the shunt resistance? Now I minus Ig is the amount of current passing through the shunt resistance into S. Okay, so this voltage is equal to this voltage. Okay, so now that implies we require the value of S. So the value of shunt resistance becomes very simple. So IgG divided by I minus Ig. So this is my value of, this is the formula by which we can easily found out. Listen very carefully. We can easily found out what value of resistance we will connect in parallel with the galvanometer to get or to convert the galvanometer as your emitter. Understood? To measure the current. Clear? Okay. So this is the value of the shunt resistance. S is equal to Ig into G divided by I minus Ig. This is the formula by which we can get the value of the shunt resistance for conversion of galvanometer into emitter. Clear all of you? Okay. So in this conversion of galvanometer to emitter, there is a important concept, that is your nothing but your current sensitivity. What is the concept? The concept is current sensitivity of galvanometer. When the galvanometer used as a emitter, then there may be a factor arises that is called current sensitivity. Okay, so let us know what is current sensitivity. Okay, so now previously in the operation or principle of galvanometer, what we will know? Now the tau, the torque produced in the coil must be equal to the restoring torque produced in the spring in equilibrium condition. So that implies from this we will know that this is your NABI is equal to C theta. Simply, okay. So that implies from this we will now modify a thing. So what we can modify? Now theta divided by I. Look at very carefully. Theta divided by I can write NAB divided by C. Theta divided by I is equal to NAB divided by C. Okay. So this is what I have written here. This is nothing but the current sensitivity, the expression of a current sensitivity of a galvanometer. Clear? And we know that what is this called? Galvanometer constant. This is called NABC divided is called galvanometer constant. Just previously we know. So that's why the theta by I is called the current sensitivity of the galvanometer. This is the expression. Suppose I will name it equation number 1, 2, 3, anything you can take. So let us take equation number 1. Okay. So this equation number 1 is nothing but the expression of your current sensitivity of a galvanometer when the galvanometer used as a emitter. Clear all of you? Okay. So now look at very carefully. So what is the unit here? What is the unit of current sensitivity? The unit of current sensitivity is theta is radian and I unit is ampere. So radian per ampere, very simple. So the unit is radian per ampere. The SI unit of this current sensitivity becomes radian per ampere. Okay. So now how we will increase the current sensitivity? You can now visualize from here. How we will increase the current sensitivity? By increasing the number of turns, by increasing the area of the coil, by increasing the magnetic field. Whereas by decreasing the couple per unit twist, we will get maximum current sensitivity. Clear? Because it is inversely related. All these three are directly related and this is inversely related. Understood all of you? Clear? Okay. So this is your current sensitivity when the galvanometer used as a emitter. Clear all of you? Now the last part we will cover. Now we will know how the galvanometer can be used as a voltmeter. As a voltmeter. Now galvanometer, how it can be used as a voltmeter. Let us verify. So for this, what we will do? Simple. When we will convert it to the emitter, then what I have done? Now I have connect a small resistance in parallel. Here we will connect with the, so this is a galvanometer G. We will connect a larger value resistance in series. Very carefully. So what we will do? Now we will connect a larger value. Previously the shunt resistance become very small value, but here we will take a larger value resistance which has to be connected in series with the galvanometer. Okay, so now suppose the Ig is the current flowing through this galvanometer, and here we have to find out the voltage in between these two. Okay, so now similarly I have to apply what? Now I have to apply the KVL. So similarly I have to apply the KVL to the circuit. So what I have to apply? The total voltage V is equal to the voltage across this plus voltage across this. So what is the voltage across this? Ic into Z plus. What is the voltage across this? Ic into R. Understood? Okay, so that implies our aim to find out the value of R. As in the previously, from the formula we are getting the value of S. Similarly, here we have to find out the value of R. So for this, what I have to do? Now I have to find out the value of R. So that is IZR is equal to V minus IGG. So that implies what is the value of R? The R is equal to V divided by IZ minus Z. Okay, so this is the value. All clear? So now this is suppose equation number 2. So this equation number 2, from this equation number 2, what you will get? From the equation number 2 we get the value of what value of resistance we have to connect in the galvanometer in series, so that the galvanometer used is a voltmeter. What is the value? From the formula I can get the value of the resistance. Understood all of you? Okay. Now, when I will compare these two structures, previously I have done galvanometer as emitter. Here now I have done galvanometer as voltmeter. What is the difference? The difference is that in the first we used a resistor, a small value resistance in series, and in voltmeter we use a larger value resistance in parallel. This is the main difference. Okay, so during this conversion, here also an important factor, that is voltage sensitivity. That is voltage sensitivity. How you will get the voltage sensitivity? So what is the value of current sensitivity I will get? The current sensitivity is nothing but theta by is equal to theta by I is equal to ABN divided by C. Okay, so this is my current sensitivity. So to convert it, let us divide 1 by R on both sides. So theta by I into 1 divided by R. Here also ABN divided by C into 1 by R. Very simple. So now look at all of you here. IR, we know that from the Ohm's law, V is equal to IR. So I can write theta by V. That is equal to ABN divided by RC. Clear all of you? So this is nothing but your voltage sensitivity. The previously I have derived the current sensitivity. This is the expression of your voltage sensitivity. Okay. So what is the unit of current sensitivity? Radian per ampere. And what is the unit of voltage sensitivity? Radian per volt. Understood all of you? Clear? Clear. So this is how the galvanometer can be used as a emitter and how the galvanometer used as a voltmeter. This is a very important question from the exam point of view. Go through this very carefully. If you have any doubt, then you can contact with me. I think all of you clear. This is the structural part. Okay, and this is how the conversion of galvanometer as a emitter and as a voltmeter. Clear, dear students? Thank you so much for this now. Okay, have a good day.